trivial. So then it's just a product of one fixed manifold with the base B. And then you can use it to study a family of line bundles on the same manifold. And you can use it to study the variation of complex structures on those line bundles. They will always be topologically the same, but the complex structure on the line bundle might vary, and you can get that. And finally, you can also use it to study the case when the fibration is trivial, and the complex line bundle, the complex structure on the line bundle does not change either. So the line bundle is just a pullback to the total space of a fixed bundle on X. So beautiful X is like this. I take a fixed bundle on that one. I pull it back to the total space. So I get something which is the same on all fibers. And the only thing then that changes is the metrics on the line bundle. So you can use it to study variations of metrics on one fixed line bundle over one fixed manifold. So almost equivalently, it can be used to study the variations of Kähler metrics. Omega t is IDD bar of phi t. Phi t is the restriction of phi to LT. So instead of looking at the metric itself, you can look at its IDD bar, which is a Kähler metric, and you can look at the variations of those metrics in the Mabuchi space of metrics. I'm not going to say very much about that, but it's just a remark that in a special case when B here, the base, which I took to be one-dimensional, when it is a strip like that, and you assume also that the metric depends only on the real part of the variable, so then you have a real curve. The metric on L here can be viewed as a curve of metrics on L prime. And then the C omega actually has a description as the geodesic curvature of this metric in the Mabuchi space. Okay. Now, to get a little bit closer to what I'm going to talk about now, there is also an analog of the second theorem for the negative bundle minus L. So you look at the dual minus L of L, which is now a negative bundle instead. I still assume that L has positive curvature along the fibers, so minus L has strictly negative curvature on the fibers. So now this is about, then the theorem is about the dual bundle, E star, whose fibers then, the dual of Hn0 with coefficients in L is the space H0n with coefficients in minus L by serduality. And the conclusion is that this bundle now has negative curvature instead. Because E had positive curvature, so E star has negative curvature. So let's look at an example of that. What's that supposed to say? Well, one thing is we can look at the simplest case, which is when the fiber dimension, the relative dimension, which is the fiber dimension, is equal to 1. And then we can take L to be canonical bundle on each fiber, which just means that L is the relative canonical bundle, all of L. And so now we're assuming that this is positive on fibers. The metrics are positive on fibers. So this means now the fibers are compact Riemann surfaces, and the canonical bundle positive means that these Riemann surfaces have genus at least 2. So we have a family. Our total space is a family of Riemann surfaces of genus at least equal to 2. And then you can now look at, instead of H0n xt minus LT, now becomes H01 xt, and the dual of the canonical bundle is now, the canonical bundle is just a cotangent bundle, so you get a tangent bundle. So you get a T10 of the fiber xt. I should have written that. Now, this is precisely where the Kodaira-Spencer classes live. As we had before, the Kodaira-Spencer classes, they lived in exactly this H01 of a manifold with of a fiber with coefficients in the tangent bundle of the fiber. Now we can take, in this case, phi t to be the potential of the Keller-Einstein metric on xt. And you also have to well, I skip over that. You have to be a little bit more precise there, but let's forget about that. And then the norm, the L2 norm that you get of an element in here will be the Weil-Petersson norm of U. If you unwind the definition, you see that it's the Weil-Petersson norm of U. So you have a formula for the curvature of the Weil-Petersson metric. You get an explicit formula. From the general formula for the curvature of such twisted bundles, you get a formula for the curvature of the Weil-Petersson metric for a family of Riemann surfaces, which was first obtained by Wolpert in 84, I think. Yes. So now, if we combine this with the theorem of Schumacher, the theorem of Schumacher says that C omega in this setting is greater than or equal to 0. Then you see that my first bundle had a positive curvature, and so we get that the curvature of the Weil-Petersson metric is negative then from this. And this was first proved by Alfors. Actually, you can discuss which sort of negativity property you have of the curvature, but I will not go into that either. Okay, this is what happens when you take fibers to be of higher dimension than n. Looked at by Siu shortly after Wolpert's work. So he on metric. No, not for n equal to 1. That's what Wolpert did. It's for n greater than or equal to 1, sorry. For higher dimension of the fiber, he looked at the Weil-Petersson metric. So we're looking at the family now. We're assuming the canonical bundle is positive. Then by Yau's theorem, the Aubin-Yau theorem, we have that there is a Keller-Einstein metric, and you can use it in the same way, and you get an L2 metric on those spaces. And Siu found an explicit formula for the curvature of this Weil-Petersson metric. I will come back to this explicit formula in a little while, but he found an explicit formula for the curvature, which is naturally a little bit more complicated than in the one-dimensional case. Okay. Now, you can connect this to the bundles Hn0 that I discussed before by looking at a vector bundle, well, a bundle En0 that has those fibers now. So you should notice now that I'm still looking at n-forms, holomorphic n-forms, but they take values in the negative of the canonical bundle, which is negatively curved. So n-forms with, but n-forms with values in the inverse of the bundle of n-forms, it's not so much, so it's just C. So it's just C, and actually the whole bundle is trivial. But I'm going to use this interesting trivial bundle quite a lot. So Hn0 here is just C, and the whole bundle is 0, is trivial, and you can take a trivializing section, U0, which is then between friends equal to 1, but it's 1 viewed as an n-form with values in the bundle of, in the inverse of the bundle of n-forms. Now I can take this U0 and I let my kappa operate on U0. And then I get a cohomology class in Hn minus 1, comma 1. This increases the barred index 1 unit and decreases the unbarred index 1 unit. So you land there. And you can check now that actually the Weil-Petersson norm of the kappa here is equal to my L2 norm of U1. So Siu's formula can be viewed as a curvature formula for this bundle, En minus 1, comma 1. So En, comma 1, yeah. So En minus 1, comma 1 is the bundle that has those as fibers. Yes. So, and this now suggests that you look not only at that one, but you look at EPQ. So it's a bundle with whose fibers are HPQ, with values still in the negative of the canonical bundle. And you endow it with the L2 metric that you get from Keller-Einstein metric on this, Keller-Einstein potential on this. And we also assuming that P plus Q is equal to N now. And then Schumacher generalized Siu's formula and got the curvature formula for all those bundles here, E, P, Q. So, and now I'm coming to the joint work with Mihai and Siu. And we generalized this theorem as follows. I'm going to write down now a horrible formula. Well, horrible statements. It takes some time to digest, maybe. Let's see. So we have the same situation as before. We have the total space and the smooth proper fibration. And we have a Hermitian holomorphic line bundle there on the total space. And we are assuming that it is strictly positive on zero, strictly positive on fibers. I assume still that P plus Q is equal to N. And I assume that all the space, I assume that all the spaces, all those spaces for all different fibers have the same rank or the same dimension. Then the statement is that they form a vector bundle that I call EPQ. I can give it the L2 metric induced by this is the L2 metric on, this is the metric on LT, and this is the IDD bar, which gives you a metric on the base space. You need both of them to define the L2 metric on those. And then you get a Schoen connection, and it has a curvature, and that curvature has this formula. I'm going to explain what it says later. This was supposed to come out in red here, and I will explain why this should be red, and all the other ones are black here. Because in this situation, you would sort of like the curvature to be negative. Now you changed all the signs. Before we had a vector bundle of positive curvature. Now you expect to get something of negative curvature. And this one is good. It looks just like before. It's whatever mu is, it's something negative. And this is also negative, and this was negative if you know that C omega is strictly positive. But this is the only thing that has a plus sign there. And this is exactly what happened in Siu's work also and in Schumacher's work. But I should say what all those notations mean then. I'll tell you what almost all the notation means. So first, the eta here is the same as in a theorem in the beginning. It's what you get when you take, so the eta is the bad guy over there, is that you take U in the fiber and you operate with the Cordera-Spencer on that. Then you get a form and you get this. So this is more or less what we had before for HN0. And then Xi is almost the same thing, but you take the conjugate of kappa phi instead. Let it operate on you. And then you wonder maybe what the H here means. H means that you take the harmonic part of that form. And the perp here means that you do not take the harmonic part. You take only the component that is orthogonal to harmonic things. So now I have explained everything except what mu is. Mu can also be formulated in terms of those things here, but it won't play a very big role in the sequel, so I will just regard it as an extra bonus. It has the good sign. It makes things better, but we're going to focus on the other things there. And the same formula was obtained independently with a different proof by Philip Naumann. Right. So let me say something about this. One comment about the proof then. So you want to know something about the curvature of those bundles. And that amounts basically to computing IDD bar of the norm of a holomorphic section of the bundle. So in order to compute curvatures, you want to compute second derivatives of norms. And U depends on T. Now it's a holomorphic section. And T, the norm also depends on T. So if we go back to my favorite case, the earlier case when PQ was N0, you look at N0, then we had a nice formula here for the norm. It was just the integral of u bar essentially over xt, which we can also view as the push forward of a form. You can look at this thing, u wedge u bar, as a form on the total space, and then you push it forward in the sense of currents, and you get a function on the base, and that thing is this. And now if you want to compute IDD bar of this, you can use that IDD bar commutes with the push forward. So the D and D bar, they enter into there, and then you do some manipulations, and that's how you get the formula. If you are in the PQ case, things are a little bit more complicated because there is no such simple formula for the norm when you have PQ forms. You cannot just say that the norm of a PQ form is the integral of u wedge u bar, because you will have positive and negative contributions. But there is, the following lemma says that in our situation, things are not so bad. So this is a lemma independent of all the rest here. It's probably very well known, but maybe it wasn't to us. So if you take a compact manifold, one single compact manifold, which will be one of the fibers, and it has a line bundle, which is with strictly positive curvature, and you let U be a PQ form with values in minus L, and you say that it's harmonic for all those data here. It's harmonic for the metric Q that's induced by phi. Then the conclusion is that U is primitive. So it means, since it's an N form, primitivity means that omega phi wedge U is equal to 0. So that's the sort of primitivity that appears in Lefschetz decompositions and such things. And why is that good? It is good because for such primitive forms, you really do have the same simple expression of the curvature. It's basically still just the integral of u wedge u bar. But you need to have another constant in front of it here. It changes to plus or minus depending on Q. And then you can still write it as the push forward of a form on the total space. And you can still take IDD bar, etc. And the same principle of proof as in the N0 case applies. There are some complications, but the same basic principle appears. So much for the proof. And so let's now look at the formula again. So let's just see what the formula says in practice, so to speak. So there's the formula again. I just repeated it. And if we take L equal to the negative of the canonical bundle, and you take phi to be the Keller-Einstein potential. So here L was arbitrary and subject to some condition on the curvature. But let's assume now that it is the negative of the relative canonical bundle, and phi is the Keller-Einstein potential. Then this is the same formula as Siu and Schumacher had them. If the fibration is trivial, then this thing here, the bad guy, disappears because it's the harmonic part of the Cordera-Spencer, and it will be 0 then. So in that case, you will get that the curvature is negative. And we also see that if U has the good taste to lie in the kernel of this operator, didn't come out so nicely, but this operator is the cup product with the Cordera-Spencer class. If it does, then eta is still 0 because eta was precisely this thing applied to U. So then this will still be 0, and you get that in the curvature, in the kernel of this thing, the curvature is negative. And you also see that when P, Q is 0, n, the curvature is negative, because then the bad thing will vanish for bi-degree reasons. It will be an 0 n plus 1 form on the fiber, which must be 0. So then the curvature is negative, but that is more or less what we already knew then, because that's the dual of the first theorems on positivity of direct images. So here, it's since we are taking the harmonic part of eta, it amounts to looking just at the cohomology class of kappa acting on this. Now, you can apply this formula, in particular, to those sections here. We had my favorite section, U0, which was just equal to 1. And then you apply kappas successively. You get U1, U2, U3, etc. And then you take the, so it's well known that these will be holomorphic sections of the corresponding bundles. And then you can take, you define functions here, phi q, which are the logarithm of the norm of those. And then it follows from the formula with a little trick introduced by Tu and Young, that you actually have this inequality. So you don't have negative curvature would say that IDD bar of this would be positive. It's not positive because there's this term and this one. So you have both of them. But you have this. And you should interpret this when q is equal to n. You should interpret this one as minus infinity, so the last term disappears then. Okay. From this one sees then, so this is a variant of an argument by Tu Young and Schumacher, that you can take a combination of those with positive numbers, such that you get such that this defines a metric on the base with the curvature bounded from above by a negative constant. So by summing up here, it's not exactly what they did because I'm taking the logarithm here, but you sum up here with certain coefficients. It's a telescoping series on the right-hand side, and if you adjust the coefficients here in a good way, you can get that IDD bar of this will be greater than IDD bar of phi q. Well, the sum of a combination of phi q will be greater than e to this combination of phi q. So you get strictly a negative a metric of strictly negative curvature, which basically says that the base cannot be all of C. And with more work, then one can see that this means that if you look at the case of a general base here, Y cannot contain an entire curve. Okay, there is yet another formula here. Oops. There is a variant of this curvature formula for the case when it's actually more or less the opposite case to what I had before. So I'm not assuming now that phi is strictly positive on fibers, but instead 0 is the opposite case. So let's assume that the line bundle is flat on all fibers. Then the curvature, then you can compute the curvature of phi. It's not hard to see that it's a pullback of a certain form on the base. And then we have the following theorem. We get the curvature formula for those bundles in that case, that the curvature in this case is equal to, is this. So that's the case when the metric on the fibers is flat. So special case of that, a special case of that is when you take L to be just a trivial bundle. So then this is a formula of Griffiths. Then the C here will disappear, and this is Griffiths' formula for curvature of Hodge bundles. But now instead you can take to be the relative bundle again, and the fibers to be Calabi-Yau, and it's flat. You take a metric which is flat, and you construct easily a metric on the fibers which is flat. It's the Bergman kernel metric, and you get a picture which is very similar to the canonically polarized case. But now it's a family of Calabi-Yau manifolds instead. Okay. So there is one point here that I have glossed over a little bit. There was an assumption that I inserted in the theorem that the dimension of all those spaces does not depend on T. So it can be justified, I think. No, it can be justified, but yeah, I'm not an expert on these matters. But let's see, let me try to explain it in writing. Oops. So here's the explanation. So you look at the higher direct image of. So you look at this bundle now. This is essentially the bundle of n minus q forms on the fiber, and you tensor it with our line bundle, and you take the qth direct image of that. So by a theorem of Grauert, these sheaves, you get sheaves. They are coherent, so they are locally free outside an analytic variety. And then we have a vector bundle whose fibers you can see is equal to whose fibers are equal to precisely those spaces that we had there. Maybe after removing another analytic set. So in our situation, when the basis of dimension 1, it means that basically the hypothesis that I had is satisfied outside of a discrete set. And then one can prove that the metric extends across this discrete set, or in general it extends across varieties like that to a metric on sheaves introduced by Paun and Takayama. So we still get more or less the same picture even without this hypothesis. But now, once we have extended the metric over some bad points, we can try to extend it one step further to the case when the map P there is not a smooth fibration, but just a surjective map. So it may have some singular fibers over a Zariski closed set. So it means that there is some analytic variety in the base where you don't have a fibration, and the fibers there are not smooth manifolds anymore, but they are singular varieties instead. We outside this analytic set, the previous picture applies. Now the question is if the metrics extend over the bad set. So we look at the bad set in the base. It's called delta, essentially. And W is the inverse of that. And then we are looking at higher direct images, which are almost like before, but we are now taking them not for omega is not the usual cotangent bundle now, but the logarithmic cotangent bundle, which essentially means that it has poles on the bad set W. That's what this notation is supposed to mean. And we are then able to extend our metrics to these sheaves, provided one knows something about the curvature of L.
So the relative dimension is always 1 minus 8 dimension of the total space, right?
It doesn't need to be in the end, but for the purposes of this lecture, yes, it is. They are, but it doesn't need to be. No, it won't be. Yeah, actually, in this case, when I'm talking about delta, etc., delta is going to be a divisor in the base, which may have higher dimension. The base may have higher dimension. Yeah. Yeah.
Then you assume some dimensionality of fibers?
Then we decompose. So. Yeah. We are looking at a situation where the fibers are equidimensional, but there are some bad fibers that have singularities, and actually we are assuming that they form a divisor of simple normal crossings, etc. Yeah. Okay. So now, in order to extend the metric across this bad set, the W there. We need some information about the curvature and the behavior of the metric on L near the bad fibers. So, and this is probably the place where we have most advantage of working with a general line bundle and a general metric instead of just the anti-canonical bundle and the Keller-Einstein metric, because now we can construct a metric ad hoc, so to speak, by algebraic geometric methods, and then we can construct a method whose curvature can be estimated and has the good property that we can extend the metrics over the bed fibers. And this has an extra bonus, namely that we know more about the curvature of this than we a priori know about the Keller-Einstein metric. And the curvature of the line bundle, you remember, it came in to the curvature of the direct image bundles. So, and the net result that we can do with this is a metric version of the following theorem of Wang and Schumacher. So now we have a base which is higher dimensional. We have a family of canonically polarized manifolds, maximal variation. That means just that the kappa is not zero. Well, not zero anywhere. So. Then there exists a positive number, smaller than the relative dimension, such that this bundle, the symmetric powers of the logarithmic cotangent bundle of omega, contains a non-trivial big coherent sheaf, which should be interpreted as a sort of positivity condition on this bundle. And the subsheaf that we are obtaining this way, so this by Wang and Schumacher with algebraic methods, we have a more or less than algebraic proof, even though the construction of the metric on L uses algebraic geometric methods. But the subsheaf that we get here is essentially the kernels of those of the Codera-Spencer maps that I had before. You've probably forgotten by now, but there was like in the general theorem, if you were in the kernel of the Codera-Spencer map, the bad guy in the curvature formula disappeared. So on these kernels there, you have a negative bound on the curvature. I think that is all I have to say. So I thank you and congratulations to Frontier.